set up the groups and let you know. And I'll, in a day or two, I'll circulate the assignment on the Slack channel, and it should be done as a group, and there won't be any grading or anything like that. This is just for your own learning. But what we will have is a session where all of you can present your findings from the assignment, your conclusions. So that's how we'll structure the assignment.
Alpan, may I just add one thing, please?
Sure.
Essentially, what Alpan and I just discussed, we are following this. I mean, for some of you may have done a management degree, but a lot of management learning happens through case studies and through application. So such highly applied areas, it's more useful to have people sit down, discuss with one another, and it is through those discussions that learning is maximized. And the accountability is to actually stand up as a group and present. And do expect, as part of these presentations, questions. This is like in cricket, this is like a net practice. This is like you're playing within the home ground with known people. Because tomorrow, the expectation is that we will play in the same way in a real pitch. When you go to a real pitch, you may have less of a comfort. So that's the reason we are following this technique. This is a classic style of learning, applied learning, which works wonders. I've been through this myself, and I can assure you, it's just absolutely. If you're wanting to do work, this is the best way to learn. Go ahead, Albert. Thanks.
Okay, great. Thanks, Shekhar. Can you all hear me?
Yes.
Yeah, okay. So what I'm going to do is do a little recap of what we learned last time. And as usual, feel free to interrupt, feel free to ask questions. I won't be able to see raised hands. So Joanna, if you can just let me know if somebody is raising their hand and needs to ask a question. Yeah, so we are going to go slowly as usual. Again, same ground rules. Feel free to ask any question whatsoever. So just a quick recap of what we went over the last time. First, we talked about features. And again, to remind you, features are a collection of variables that are used by the AI to predict an outcome. In statistics, these are referred to as independent variables. Although they don't have to be independent of each other or uncorrelated, they can be correlated, but we just call them independent variables. They are sort of the variables that will be used in order to predict the outcome by the AI. And we'll see examples. The labels, on the other hand, are the outcomes themselves. So a label is an outcome that correlates with the features. And labels go by different names, different terminology. Sometimes labels are often referred to as ground truth for the AI. If somebody uses the term ground truth, that's the same thing as a label. A label is the same thing as a ground truth. The point of this is that the AI, once it is trained, will attempt to predict the correct value of the label given the features. So the AI has to be supplied the features as an input. Once it's applied the features as an input, it predicts the label or the outcome or the ground truth. In statistics, these are called dependent variables, especially when you study, for those of you who studied statistics and regression analysis and so on, the label is the dependent variable, the features are the independent variables. So that's the analog, that's the analogy. Now, when we say label data, it's the collection of features and labels taken together. Both together constitute label data, right? So that's really what we mean by label data. Training, we went over this as well. It's the process by which an AI algorithm learns to create correlations between the features and the labels. So it learns these correlations. It doesn't learn to create so much as actually finds these correlations within the data, right? And the outcome of this process, so an AI algorithm, a training algorithm runs, and learns to correlate features to labels, or rather learns the correlations between features and labels. And once it stopped running, the outcome of this process is an AI model. So an AI model uh, is a piece of software which is a mathematical model of this correlation. It's fairly complex. It has lots of parameters and so on. Again, as I said the last time, it's not a correlation that can be captured with a simple number. It's actually a set of numbers, a set of what are called parameters of an AI model. Inference is the process by which an AI model predicts or estimates the label from the features. So the act of doing the AI, which is predicting outcome, predicting label from the features, is called inference. And inference is the actual usage of the AI. So the AIML team in our institute does the training, comes up with an AI model. The AI model is then used. It's integrated into a piece of software and then used, and that usage is inference. So we use the term deployment in a slightly different way from inference, even though deployment is also usage. But deployment is really the integration of this model into a software system so that the model can carry out inference continuously as features are fed into it. Right? So that's deployment. And again, I haven't talked about adoption yet, but adoption is different from deployment. Adoption is actually humans using the deployed model. Right? So you can have inference going on, which is features passed on to an AI model or inputted into an AI model, and the AI model then predicts a corresponding label. Then when you embed this AI model or integrate it into a software system, such as a phone or on the cloud, once you integrate it into a software system, so that the model is able to carry out inference continuously, that's called deployment. And when this model will actually be used by humans to create impact, that's what we call adoption. Okay, adoption is not in the glossary. Maybe I should have added it. Any questions? Let me pause a little bit. Okay, let's go ahead. Yes. Question? Sorry, I can't see. I have this on full screen, so I can't see who is raising their hand.
The question, I'll do it. Question was parameter is equal to feature?
No. No. So, okay, so this is a good question. Let me backtrack. The parameter of an AI model is not the feature. So you should think of it in this way. The features and the labels are used by the AI model to discover a correlation between the features and labels. Once it has discovered the correlation, it doesn't know anything about the features and labels that were used to train it, or the label data. It encapsulates this correlation in a set of parameters. So the parameters are not the features. In fact, in a loose sense, the model has forgotten about the features and labels. There is some research going on into sort of reconstructing training data from the model, but let's not get into that. But as far as we are concerned here, an AI model has forgotten all about the features and labels that went into creating it. But the outcome, which is the AI model itself, encapsulates the correlation using a set of numbers that are called parameters. Is this clear? The parameters are not the features. So if you've done, who's asking the question, by the way?
JK.
Alpan is JK.
Yes, JK. Yes, so JK, you know about, for example, linear regression, right? You have a set of data points and you try to fit them to a straight line. Now there are some, let's say you're doing this in 2D, so you can literally draw the straight line, and you could have hundreds of data points, and then you try to fit a straight line through them. Now the straight line is described only by two parameters: the slope of the line and its y-intercept. These are the parameters. They are not the features. The features are the x and y coordinates, actually just the x coordinates of all of these points.
Super clear, Alpan. Thanks so much.
Okay.
Alpan, I'll just add, just for the sake of an example. let's assume that the height of a person is equal to 4 times the weight of the person plus 3. Just make an assumption. It's all wrong, but just let's for fun assume it. The height of a person in centimeters is equal to 4 times, or not 4 times, is equal to 2 times the weight of the person in kg plus 7. So 2 times weight plus 7. So we are predicting height based on weight. So here, can somebody write in the chat box, what is the feature? Or you can speak it aloud. What is the feature? And what is the label? What are we putting as input and what are we predicting?
And what are the parameters also?
Yes. And what are the parameters? So let's just do first only what are the features. We are saying height is equal to 2 times weight plus 7. This is the information that I'm passing on. Forget AI and all. Forget all this. Just what Alpan has defined in terms of what is a feature in this. What is the information you are providing to the equation in order to derive its output. So the answer here is the label is the height, Malay is saying, and he's correct. The
Right.
feature is the weight, and
Yes.
he's correct. And there are 2 parameters. One is, we are saying 2x plus 7. 2 is a parameter and 7 is a parameter.
Correct.
So here is what happens in AI in very simple terms. So AI will be given weight 60, height 127 centimeters, weight 70, height 114, weight 85, height 205, weight 71, height 150. This is all that AI will get, nothing else. It's getting feature and label. Feature, label, F1, L1, F2, L2, F3, L3. Whole set. What is its job? It has to predict 2 and 7 correctly. Its job is to get to these parameters, because if it understands these parameters, its job is to construct an equation 2x plus 7. In order to construct 2x plus 7, x is an input. It doesn't have to say anything about x. What does it need to know? It needs to know, is it 2x plus 7 or 3x plus 2 or 17x plus 95? Or pi x plus 4000, we don't know what it is. That is it. So that aspect of getting a whole set of features labels, and somehow magically, the AI is able to come out with the number 2 as a parameter and come out with the number 7 as the parameter is the exclusive job of AI. So these parameters are called the learned things. This is what AI is supposed to be.
Yes. And usually, so Shekhar has given a very simple example just to give you an idea. A typical machine learning model, a classical machine learning model, will contain hundreds to thousands of these parameters in order to describe the relationship. And a neural network model could contain millions or billions of these parameters.
And the question is, parameters can be negative, features positive only? No. Features can also be
like that.
Features can also be negative. The label, everything can be anything. Alpan, you can correct. Sorry.
Yeah. So the features can not just be negative and positive. They can be negative, positive. They can also be categories like red, blue, white, green. Then they can be ordinal variables as well, which is they just describe an order relationship. Ranks, like ranks, first rank, second rank, third rank, and so on. So there's no restriction on the features at all. And the labels also can either be categories, like this is a pest, this is this type of pest versus this is that type of pest, and so on. Or they can be numbers, any kinds of numbers.
Again, just for the concept to be clear, because I know it's useful. So if you're assessing temperature in a place, if your output variable is to predict the temperature, the moment you hear predict, think of it as a label. So you're predicting temperature. Temperature can be negative or positive, no? So if you're predicting temperature based on, let us say, height above sea level, Height above sea level can also be positive or negative because you can predict the temperature below the surface of the sea. So if we use the surface of the earth to be 0 and if we use positive to be above the earth, so Himalaya will be, what is it, 8848 meters, something like that. And then you'll get to the depth of the ocean. I think the depth of the ocean is more than that. Maybe it's 17,000 meters, something like that. So one is minus 17,000, one is plus 8848. And the temperature in both of them presumably will be minus several degrees centigrade, I suppose. I don't know. I don't know what it is below the surface of the sea, but you can have positive and negative both in labels as well as in features. Thanks. Alpan, go ahead, please.
Sure. So this is a schematic explaining how AI works. So just look at the left part of the diagram first. You have, as I've explained, you have a set of features and you have a set of labels, and they are input into an AI algorithm. AI algorithm goes through a training process where it learns to correlate the features to the labels and outputs an AI model, which is in the blue circle. What is the function of the AI model? An AI model will take any set of features, which I'm calling here new features, as an input and output a predicted label. And that process is inference. Once that's integrated into a software system, it's called deployment. Clear to everybody? Very important to understand this, at least at a high level. Right? Now, the right part of the diagram just shows examples of features and labels. So you've got, so in actually two examples here, and I'm sorry about the way this is organized. It's not organized very well. So for example, in the first example on the top, the label is the type of flower. You know, is it a rose? Is it a lily, etc., etc. And the features are various numbers corresponding to sepal width, sepal length, petal width, petal length. So let's suppose your AI problem is you're given all of these numbers, you're given these features, namely sepal width, sepal length, petal width, and petal length. And from that, you are asked to predict the type of a flower. And that's what the AI will try to do. It will try to learn the correlation between the type of the flower and these features. Similarly, the example below, example below, you may have to predict the type of a house, you know, whether it's a 1-bedroom, 2-bedroom, is it a bungalow, is it a villa, is it a row house, etc., etc., from various features like the size, the number of bedrooms. Sorry, number of bedrooms here is a feature, not a label. Number of floors and the age, right? You may want to predict what kind of house it is. Right? So those would be features that have some correlation with the label or outcome. Any questions?
Yes, sir. Srinivas here.
Yes, Srinivas.
Yeah. With respect to pest management aspect that we are deploying,
Yes.
so we are taking input as a pest image, and based
Yes.
on ETL, we are giving the advisory. Is it called as a prediction or?
Good question. Is it called as a prediction? Because you're not really predicting anything. You are just seeing
Yes.
something on a piece of
Yes.
paper. Yeah.
Yes.
So you could call it a prediction. You can sometimes call it an estimation or interpretation. I'm using these words sort of interchangeably for the AI. As far as the AI is concerned, the dependent variable here, what it is trying to estimate or predict, is the number of pests on the track, right? And the independent variables, what go as input, is the various characteristics of the image. You know, what is in what color, in what pixel, etc., etc. So I'm not using prediction just in the sense of predicting the future. It's also used in the sense of estimating something. Yeah?
Yeah, that means we will not call it as a prediction in terms of pest management.
Yeah, it's not, yeah, we're not trying to predict the future in the sense for that particular problem. It's similar with a project like anthropometry, where you're trying to estimate the weight of a child using visual information as features, right? So there the label is the weight, the features are the visual constructs that you get from the video. and there you're trying to estimate. But as far as the AI is concerned, the mathematics works exactly the same way. So we generically call this a prediction process.
Question.
Yeah, thank you.
Question from Malay Alpan.
Yes.
So AI algo comes before ML? Question mark.
No, they're not separate things. So we use the words AI ML fairly interchangeably here. The AI algo is the learning part, and so it's okay to call that learning or training. That's all the same. Second question.
So what's the difference between algorithm and model in that case?
No, the
Or
model is the output of
algorithm.
the model is the output of the algorithm. It's like this. Again, let's go back to fitting a straight line through data.
Mhm.
There is a computer process. So usually you just do this in Excel. You don't do this yourself, right? In Excel, you type some function, which is linear regression or something, and there's a computer program that runs in the back end that finds these parameters, like 2x plus 7, right? 2 and 7. So 2 and 7 are the output of that program. But the program that is actually finding the parameters is the training algorithm. Whereas the parameters 2 and 7 constitute the model.
Well, Alpan, I want everybody to understand this. So let's stay on this for a minute.
Yeah.
This is such an important aspect. The computer program that actually runs by taking thousands of examples of weights and heights, and finally somehow magically comes to the number 2 and 7. That is training.
That is training.
Inside that, the technique that is used for it to come in 2 and 7 is the algorithm. Correct, Nalpan?
Yeah, the technique is the algorithm.
The technique. I can do different techniques.
And the output of this, the numbers 2 and 7 are the model.
Are the model. So what does it have to give? For me, as an external person, now I as an external person don't need to care about thousands of input and output. I don't care about all that. As far as I am concerned, I am going out to the world. I am a normal person. I have to go to the world. And I have to estimate the height of a person based on the weight of a person. I only need two things in this particular example. I need somebody to tell me, boss, what do I multiply the weight by and what do I add to it? So I need those two parameters. Those parameters are the model. And in the simplest example, you can extend this to whatever you want, but it is pretty much the same. Somehow the computer program that I use, so what can I use in my computer program that I use? I can call a program which returns to me. I can give it a weight input, a new weight input of a person I have never, I don't understand AI, etc. I am just being given a model and told, boss, use this model, give it the weight, it will tell you the height. That's all I'm told. I don't care about anything else. So what do? I give it the weight, it gives me the height. Inside it, the model contains this 2 and 7 in our example. How did it come to 2 and 7? The algorithm and the training that took place spent a lot of time in order to crack this problem. Why did it give 2 and 7? That is the problem of AI/ML. They have a certain technique in which they come to. They have a way by which they come out with 2 and 7 instead of 7 and 18 or 27 and 85 or whatever. Why do they come to that number? Their problem. They understand how to do it. Once you have that, you can happily go out to the world at large, armed with this information, and say, I can predict height. Because you have a model to predict height. What is your model? That equation, 2x plus 7. What are the principal aspect of the model? A feature has to come in. It's identical to the training feature. You cannot at that time say that, I want the head circumference or the stomach circumference. You cannot change all that. You have to use the prediction using exactly the same thing that you trained. Not one thing can change. Very interesting for practitioners because what you see in the real world, therefore, has to be the training features provided to Alpan. You cannot. So if in the real world you're seeing these features, you cannot train the model using some contrived inside lab features. Because if outside world is different, how are you going to apply it, boss? Not going to happen.
Yeah.
It has to be exactly the same. Am I right, Alpan?
Yes, so it has to be exactly the same type of feature. The numerical values can be different. So just to give you an example, continuing this height weight thing. So Shekhar, the example you gave was predicting height from weight, right? Or weight from height.
Height
I
from weight.
forgot. Height from weight. So weight is the input, height is the output. Weight is the feature, height is the label. Now, suppose I train an AI algorithm to be able to predict height from weight, meaning it gives me these numbers 2 and 7 and a set of instructions about what to do. So you take 2, add to the multiply to the weight, add 7, that gives you the height. Now, instead, in the real world, when I want to use it, the user tells me, but I don't know the weight. I only know the chest circumference. From that, you give me the height. This AI model will not be able to do that because it is expecting a weight as an input. So then my answer will be, well, in order to do that, you have to give me data about lots and lots of examples of chest circumference and height. Then I'll be able to create a different AI model that will do this for you. But this AI model is not going to be able to tell you height from chest circumference because it was trained to predict height from weight, not from chest circumference.
And just to jump to a real life example, this is the reason there is a lot of annoyance or pushback when, say, in LFU, if you are doing one type of prediction with one type of input, from AI/ML perspective, the entire process of working their whole project gets fully redone. Fully redone. If you tell them, no, I want one small addition. I need something else to give you as input. If you do that, keep this forever in your mind. You are starting a new AI/ML project. The moment you change, later on, Alpan will discuss measurement also, but the moment you change the features, you are creating a new AI/ML project. 3 months, 4 months, it will take because data collection will happen, internal teams will have to work, the whole thing will have to do. Full work is required in that. So, an important learning, you have to firm up your feature set. You cannot change your feature set constantly in the middle of the game. Now, when you do image and all, it is obvious, it seems easy. But when you do other things, you require deep analysis to make sure that your feature set is reasonably correct, total, and appropriate from a real world perspective. So that when Alpan creates a model and gives it to you for deployment, at that time you do not come and say, you know what, we thought we can get these features, but we are not able to get it. That is a guarantee. That means the AI/ML project has failed. The whole outcome has failed. The institute has wasted its money, $200,000, $300,000, solving a problem that is not going to work. This is such an important point for you to understand. So in Alpan's example, where he said chest circumference, that means suppose you spent 4 months working on this to get the height from the weight. That means that entire work is wasted work. So no use to anybody. Therefore, you will often hear Alpan saying, be clear upfront, be clear upfront, because the consequence is very expensive. Okay, Neha is asking. So in eSanjeevani project, we get patient data, in parenthesis features, diseases, labels from existing systems like WebMD, SNOMED, etc.
Yes.
This information, when fed into the algorithm, will train to identify the correlations.
Very good. Yes.
Thus, when a patient feeds info, the AI model will be able to make a differential diagnosis on the basis of what it already knows. Question: when a patient feeds in new info, which the AI model has not found, does the AI model make zero recommendations?
Okay, good question. Very good question, actually. So this gets into an area of AI known as generalization ability of an AI model. So again, I would ask you to think back in terms of fitting data to a straight line. And hopefully all of you understand that analogy, that you have a bunch of data points, X, Y, data points and then you fit a straight line through them. Is that example mostly clear? So yes? Yes or no?
I think most folks have forgotten, MX plus C and all that. So
No,
it's
no,
just-
I am not going to get into MX plus C or anything like that. Just you have a bunch of data points and you want to fit them to a straight line. Now you fit the straight line. Now the analog of your question would be, now suppose I take a data point that has a new value of X that I have never seen before, that the model has never seen before. Will it still be able to predict a Y? Or in the context of what Shekhar was saying, suppose in order to find those numbers 2 and 7 for getting to height from weight, it used 100 different numbers in order to find those numbers 2 and 7. But now you plug in a value of weight that is different from each of those 100 numbers. Can it still predict a value for the height? And the answer is yes. That's the whole point of having a model. If it couldn't do that, then you wouldn't need a model in the first place, because if there is an identical value to what the AI has seen before, then it already knows what is the label for that identical value, because it has seen it in the training data. You wouldn't need to do any of that training process or anything like that.
And to add to Alpan, Neha, first, all your conceptualization is totally correct.
Yeah.
The only addition that you have to make is what Alpan said. So I wanted to just think about this carefully. What is AI doing when it gets these 100 patient data with weight and height? What are the choices that AI has? One thing that it can do is memorize this whole thing. No, it can mug it up. It can keep it in the back of its mind. 2 ones are 2, 2 twos are 4, kind of. It can just mug it up and learn it. When it does that, then that means as long as you give the left, it will give you the right. That is not the way AI works. There is some theory in a different way. We'll not come to that, but that's not the way AI works. The way AI has to work is somehow it has to remember what AI does. It uses these 100 examples and comes to the conclusion, oh, when I look at all these 100 examples, the best way I can determine the height of a person is to construct an equation saying 2x plus 7 gives me the height of the person basis weight. Once it does that, then those 100 examples are forgotten. You only have 2x plus 7. At that point, you really don't care whether x is part of that 100 or not. It can be totally different, up to infinity. It can be 5,000, within reason. Height, etc. is within reason, naturally. But you can do any number, any real number, because you may get 75.3, 68.2. You can do 68.27, 17.82. It really doesn't care. This is the whole goal of AI. The whole goal of AI is to take these examples and convert it. I'm simplifying it for people. Converting it into some form of usable equation which is under the covers. I want you to understand. You will not see 2 and 7 in your life. When you use AI, you don't know 2 and 7, because in a simple straight line it is 2 and 7. But if you do deep learning, there are maybe 1 million parameters. Where are you going to track all this? It will be 2 times x1 plus 17.5 times x2 minus 16.8 times x3 plus 17 times x4 plus. It will go on to 1 million numbers. Where are you going to track all this? You will not know anything. You don't need to know anything. All you need to know is from feature, it finally gives an output. So Janak had a question. Sorry. Neha,
Yes,
was the
Janak.
question answered? First, Neha.
Yeah,
was the question
Neha, is
answered?
this clear that
Yes.
there's a small corollary to your question, which is how accurately can it do this? And this is called the generalization ability of the AI. We'll talk about that a little bit later.
Alpan, just a follow up to this, that
Yeah.
even with this, you would need enough examples within that
Yes.
range, right? Like when the data that you're feeding in, you have to give sufficient examples.
Enough sufficient examples, in the range, but they don't have to be identical. That's
They don't have to be identical, but they have to be
Yes.
within a. Okay.
yes.
Got it.
Yeah.
Yes.
One. Sorry.
Yes, Chandra.
Sorry. Go ahead.
Yeah. No, go ahead.
Okay. No, just one question based on what you and Shekhar said, right? And based on what Srinivas also asked. if we were to divide our pest management, the action taken on the ground into three buckets, right? One is taking the picture, second is algorithm counting and classifying the pests, and third is giving the recommendation based on the
Yes.
inference made. If we
Yes.
were to change parameters in the third bucket of giving that recommendation or advisory to the farmer, in which that is based on readings done 3 times or 3 days continuously in a week rather than once a week, that I
Yes.
guess we do
Yes.
now, how
Yes.
much would that involve reworking the entire system? And is our
Okay.
model currently trained to handle such a change?
Okay. So for that particular problem, the pest problem, the third part of it, so AI doesn't enter the third part of it at all. What we do is we have the AI simply counts the pests. Okay. And once we have the number of pests, then somebody from an agricultural university tells us, if you have this many pests, then this is the threshold for, uh, sorry, what they tell us is for each location, what is the threshold number of pests in order to spray. That's what they tell us. So there's no AI being used there at all. So now, if the third step is changed, and either they tell us there is a different threshold number, or we average the counting over 3 times a week or something like that, we don't have to redo the whole AI system. But that's just because of the way it is currently set up. If it were an end-to-end AI system where we would actually be giving the spraying recommendation based on our own AI, then it would be different. But we don't do that. One of the reasons we don't do that is because we don't have labels for the spraying. Whether somebody has done accurate spraying or not.
I'll add to what Alpan said from an engineering perspective. So what Alpan's saying is very important. Remember, and Janak, your question is very relevant and important because it defines the scope of the AI problem. So in agriculture, what is the scope of the AI problem? The AI problem, not the whole problem, the AI problem. The scope of the AI problem is one line. I will give you an image, give me the count of number of pests. End of story.
Yeah, that's it.
That's it. Now, when the number of pests goes in, Pranav Goel and team, Pranav Goel and team is Pranav Goel. So Pranav Goel, what he will do is he has a rule-based system. He will have, that's a classic software-based solution. You may look at sowing date, you may look at X, Y, Z, other parameters, which is put into a rule-based system, whose one of the inputs into that rule-based system is number of pests. Another is state you are deploying, because Karnataka may say 5 is high, Telangana may say 17 is high, etc. So this is a classic rule-based software system that uses the AI output, because AI had only one commitment. That is, I will give you an image and they will give me a pest count. Nothing else it is responsible for. And so then a rule-based system comes in and takes this and presents it in an appropriate rule-based manner, along with Ayushi's magic of whether you provide a voice-based input, colors, a visually interesting way of looking at it. Alpan brought an interesting point. If you change the problem definition, I want everybody to really understand this. You can change the problem definition. How will you change the problem definition? You can say, you know what, I really don't care about pest count. You can change it in 2 ways. I will give you 2 ways of changing this. One way I can change it is, I don't care about pest count. All I care about is, once I give an image, tell me whether I should spray or not. Now what you have done, your input is still the image. In the earlier example, when you gave the pest count, what was your output? It was an integer number of pests, ideally. It can be a fraction, but it's kind of crazy. Maybe a part of pests, leave that aside. An integer number of pests. You will say, image dekhiya 5 pests, image dekhiya 0 pests. It cannot be negative, it has to be actually a whole number. Integer dekhiya 9 pests, integer dekhiya 14 pests. This is the first approach. Second approach is what? I've given an image and I'm telling that spray. Given an image telling don't spray. Given an image saying spray. In this, the label is spray and don't spray. And you need to capture that ground truth. You need to have thousands of examples of images and whether they're spraying or not spraying in order to get a new AI model. And in that AI model, what happens is all these real life factors, because assume that they have taken now this is ground reality. It's nothing to do with AI. This is all program work. In that ground reality, when the person took the image of the pest, and in the ground reality, these are, forget AIML, these are people, farmers. They take the image and then they decide that, I have to spray. I want you to really understand this carefully. When they have taken the image and done the spraying, the real world activities have already occurred, which caused that image to show a certain number of pests. And what are those real life activities? The climatic conditions have changed. The sowing date is involved in this. Whether the farmer went or not, whether the water was good or not, everything is hidden inside the real life activity of the pest image and the fact that the farmer made a decision to put the pesticide or not. In this example, in one sense, the AI has an easier problem to solve. We don't have to build all this rule-based and all in that case. All we need to do is, boss, image do और बताओ कि तुम pesticide डाला कि नहीं. यही हमें जानना है. This example, and I made it simple, but in this I'm contrasting it. In this example, your assumption is all real life activities have already taken place, and you're getting very accurate information of, say, quantum of pesticide that is used. It's a different problem. Alpan, please add if I was wrong anywhere, please.
Correct. No. This is correct.
So this is the importance for problem definition. And honestly, maybe, it is so enticing that all of us will immediately think, no, it would have been much easier for us to define a problem the way I described it just now, naturally. Just give me the image and give me whether you sprayed pest or not. And as long as that is accurate, why am I, worrying about number, shambar, all that nonsense? I don't need to do all that. I can keep it very simple. And as long as and it is not a wrong thought. It is not a wrong thought to have that. It is the way you think about it. What is the risk in that? The risk is the accuracy of ground truth. Because if that ground truth is wrong, the model doesn't know anything. It knows diddly squid. It knows input features and labels. You are telling it. But if your information is wrong, which is why Alpan jumps up and down day in and day out on annotation. Because annotation converts word to digitized labels which have to be accurate, because if they are wrong, then your model will be wrong. It will not work on the ground. So I want you to deeply ponder over this, because this goes to the heart of the applied work. Problem definition. What am I solving? What am I solving has to be well understood. JK asks a question. Alpan, when the input features master list is the same for label of interest 1 versus label of interest 2, how difficult or complex is it to tailor the model for label, especially in terms of time and money, especially when everything else remains constant?
Yeah. Good question. I know you're asking this in the context of LFU. I know that. Where you have a situation where your input feature list is the same, and earlier you were trying to predict for a certain label, and now you're trying to predict for that label plus some other label or a completely different label. It is less complex than having a completely different feature list. Let me put it that way. But you still have to retrain the AI algorithm. You may end up using a very similar code base, but you still have to retrain, reevaluate, check if it works robustly. All of those things have to be done again.
Now, Alpan, I would probably be less accommodating. I would say that.
No, I'm stating it like it is. Yeah.
No, I would say, like, let me give you an example. Given the weight of a person, we predict his height. Given the weight of a person, we predict how well the person bowls. Input features list is the same. What is the amount of difficulty that is needed for you to capture information and data with respect to bowling and bowling efficacy? With respect, see, you're now introducing a totally new data collection exercise. So your input is the same, but your output could be anything. You can do weight with respect to God knows something else. I don't know how high a person can jump. These are independent exercises. By definition, for most cases, assume that the feature and the label are tied at the hip. Don't separate them. Don't assume that you can separate them and simplify the exercise. It is not true. Because the collection of ground truth is always with label and feature. It is always with, feature and label. You will get the feature and then you will get the label. So if you've got features and got labels which correspond to one aspect of a situation, such as the height of a person, then suddenly if I say how high will the person jump, you've got a complete data collection exercise in order to do that. That is why it is difficult. Then these guys may determine that the height of, they may determine multiple things. Let's look at bowling as a little easier. They may determine, you know what, the weight of a person has nothing or very limited capability to predict how well the person bowls. So even the outcome itself could be questionable, which means there's not enough distinguishing information in the features for us to make that prediction. We are not able to come with an equation at all. Alternately, they may find that, you need a lot of in-depth analysis in the existing model may not work at all. That model, that algorithm, they've used some algorithm, some internal technique of solving problem. They may decide, this is not going to work. In their world, it could be, I tried to fit a line. It could be, I tried to use a random forest. These are all technical terms used in the world inside AIML. So they may decide, this whole thing is not working at all. Decision trees, etc., not working. So don't make an assumption at all that just because you have the same feature set, you can come to another label. You cannot. Assume you cannot. If you can, it is an accident. It's a happy accident. But conceptually, as far as the program team and the systems analysts and the individuals facing the customer, communicate to the customer very clearly that if you change the combination of feature label, as far as you are concerned, it's a new project. Alpan, am I okay with that?
Yes. I mean, there are exceptions where the two labels may be related labels, and in that case, there may still be a correlation. But the two things have to be done again. One is collecting the labels, as Shekhar said, and the other is training the AI model. Has to be redone.
And the reason I'm a little stricter than Alpan is because traditionally the AML team has probably taken on a little bit more of the flexibility. But you know what happens when we do that? It's not out of various either scientific endeavor or enthusiasm or capability. We do it, but two, three things happen. One, the time becomes very long, the effort becomes very long, and we come to roadblocks. And these roadblocks are actually conceptual roadblocks that occur later in the project. But if you keep the conceptual things clear, then you don't even want to head in that direction. As far as I'm concerned, you change label, you change the project. You change features, you change the project. And if you have to communicate this to external parties, because they must understand the consequence of the impact of their decision. It also front-ends the lot of discipline, what you must do in the beginning of the project. If you can't do it, then we shouldn't even do the project. It's as tough as that, because that is the truth. That is really the truth. What happens is we accept it. Various reasons. We get excited, we're enthusiastic, the problem is nice, we are good people, whatever. Then when you actually get into the problem, all these things which you knew will occur actually occur. मुझे मालूम है ये होने वाला है और होता है. That's the worst situation to be in as an institute. I would rather tell that upfront to people. This is the reason we are wanting people to be totally conceptually clear about the way you think. Because if you come even to one wrong decision, you will cause the entire institute to work on the wrong AML problem. within the wrong AML problem, they may come out with the best result, but you know what? It's not going to be deployed. This is the heart of our learning that we must take. Rest of it, a lot of things will take place. I'll be teaching lots of stuff which will help you. But if there's only one thing you have to learn, first, I must be totally clear on my outcome, and then Alpan will discuss in detail measurements, which is also equally important. And I must be totally clear whether I'm asking the people the right questions to give me a result. Because if I do a mistake in that, I've actually killed the AML project. I know it sounds very harsh, but believe me, it is absolute truth. I'm not sugarcoating it in any manner. Then what happens? Naturally, we are human beings. We will get into the human drama of getting angry, upset, excited, worried, work harder. They are consequent things of wrong problem definition. And I know Alpan will think, I've kind of hijacked some parts of his work. So Alpan, with true apologies, but I really want people to know this part, because the rest of the things you teach are so important to learn. But if they don't understand this part, we want to not even have one error.
Yes.
In software terms, that's like defining wrong requirements. I just spoke to Alpan. It is like, I want a material management system, but I have defined a payroll system. It is exactly the same for AIML. The reason we don't see it like that is because we are not sure about AIML and we are approximate. But for AIML, even though they only speak of features and labels, the moment you change the feature label combination, the problem changes. The project is restarted. It is the same as payroll system versus material management system. You cannot do that. You cannot accommodate it later. You cannot define it by and by. You cannot say later we will find out what we must do. You cannot say let us try with this and then we will do something else in the future. Sab kuch nahi chalega. Guaranteed failure. I know Alpan has more accommodation for some of the things that I'm saying, but I would prefer for us as a team, as we face the external world, to be this clear on the conceptual fundamentals. Sorry, Alpan, go ahead.
Yeah.
And
Yeah,
thanks,
no,
Alpan and Shekhar. May I have a minute? Yeah. Thanks for the great clarity. I just asked this question for my own internal clarity, not advocating for the external stakeholders.
No. The question is brilliant.
The question is very relevant.
It's very relevant.
Yeah.
The reason the
So
question is,
please never
ask.
apologize for a question.
Yeah.
It can be, why is the sky blue is also a legitimate question.
Right. No.
We play a very neutral diplomatic role when we are facing the stakeholders, Shekhar and Alpan.
No, we can't.
Things.
But
For the same reason, I was seeking clarity. So it always becomes a different use case. I got that.
Yeah. So we shouldn't do that. We shouldn't play a neutral diplomatic role. We should really try and pin down the problem, even with external stakeholders, because they are not used to thinking in this way. So it's our job really to educate them. Because it has a lot of
your mindset helps me make better decisions while I'm talking to the stakeholder. Yeah, thanks.
Correct.
Yeah.
And JK, you are bringing out a aspect which has been endemic in our institute for 3 years. So you cannot, the joke is emperor is nude equivalent. The person who brings up an information set is doing an exceptionally good job. The prevalent conditions is what we are trying to solve. We don't care about anything else. There is a conceptual clarity as an institute we must stand up for. And we are, as some of you may have noticed, across the board slowly and systematically by getting more discipline, problem-solving efficacy, building the teams across the board, pulling in the same direction, no side talk, politics, this, that. These are all little things we have added in this institute because our mission is to solve problems to help the poor. So this is such an important problem and it is so important that you brought it up. If you had not asked the question, probably we would not have had the clarity. So the real statement to you is thank you. Because when you ask these questions, it allows me or Alpan to realize that, you know what, we need to drill down on the fundamentals a little more. Our job is only that. We are teachers, helpers, mentors. We have no other role. We have to help the organization succeed because we know what we need to do. Alban, of course, is far more talented in the AML space. So I defer to him all these matters. Go ahead, Alban. And I will not
Yeah, I
hijack.
think
Anyway,
we
I'm
are,
going out
no,
in
no,
3 minutes.
no, we are anyway at time. I think we just have about 5 minutes left. So this is the last slide I want to discuss today. We will go slow through this. I realize that this will, I mean, I was originally thinking 3 sessions, but now it's looking more like 10 sessions, but that's okay. There's no problem. We'll go through it. I won't be able to do any more sessions this week because I'm traveling from tomorrow. But next week we'll do 2 or 3 sessions. Okay. It's important to go slow and make sure everybody is comfortable with the material. So the next thing, actually, this sort of segues into what we've been talking about so far, is in terms of the problem definition. So one of the most critical aspects of defining an AI problem is, do we really need AI for this? Right? I mean, we have a tendency, not just in our institute, but I've seen this at other places as well, where just because you have data, you say, okay, let's do AI. Or somebody will say, and I'll give you an example of, we had a conversation recently where somebody asked, can you use AI to, for nutrition, where you design different diets for different populations using the same set of ingredients? Now, it all sounds very nice that you have lots of data and so on, but do you really need AI, or is another solution, another type of simpler solution sufficient, right? So remember that AI is only exploiting a correlation between the features and the labels, right? I keep on saying the same thing again and again. And correlations are almost never perfect. So the AI predictions are never perfect. If you can live with imperfection, that is one criterion for choosing an AI solution. Or if there already exists a solution that is close to perfect in terms of correlation, if there is already a perfect correlation between some features and your outcomes, then there is no need for AI. So just want to illustrate this with a couple of examples. So let's say you want to build an AI solution that predicts the risk of getting lung cancer over the next 6 years. So at any given point in time, the AI will tell you, this is your risk score for getting lung cancer. This is the probability of you getting lung cancer at some point in the next 6 years. Now, there are various possibilities, right? And these are, the first scenario is an artificial scenario, but let's assume it's true. So let's suppose that cigarette smoking is perfectly correlated with lung cancer risk. Okay. So the more cigarettes you smoke cumulatively over your lifetime, the greater your risk of getting cancer over the next 6 years. And you also know, again, this is a scenario, it's a simulated scenario. And you also know that no other factor is associated with lung cancer. It's only cigarette smoking that causes lung cancer, nothing else at all. Now, if the situation were as simple as this, then you really don't need an AI model to predict lung cancer risk. All you do is look up how much smoking has the person done, and based on that, then you can do some simple mathematical calculations to predict a risk probability. You can, etc. But you don't really need an AI solution with millions of parameters or thousands of parameters or something like that. Is that part clear? Yes, no?
Yes.
Okay. Yes, okay. Now suppose there's a second scenario, slightly more complex, where it's not one factor like cigarette smoking that's associated with lung cancer, but there are a number of factors. So it could be smoking, obesity may have a correlation with lung cancer, age, other comorbidities. Does the person have a history of other types of cancers or even lung cancer in the past? The level of education. Maybe there are all these other factors that also correlate with lung cancer. So now the correlation or association becomes complicated, right? You need to find an association between these factors and lung cancer risk, right? And the association could be high, but it needs to be learned through a training algorithm. It needs to be learned from the data. You can't just eyeball it and say, okay, it is one factor, so I can tell you what your lung cancer risk is. So this is where you start needing an AI model. And now one of the simplest AI models is a linear model, as it's called. You don't need to worry about what's a linear model. In very simple terms, it's like the model that Shekhar talked about, where you multiply the weight by a number, add another number, you get height. That's a simple model. It's a linear model. That's what it's called mathematically. You don't need to worry about that. But this type of simple model may work as a first try. And in fact, such a model exists in the literature. You can look it up. So there's a model that was made in 2012 that's called PLCOM 2012 for predicting lung cancer risk. And it's a simple web interface. You input various things like age, your BMI, I think level of education, history of smoking, etc., etc., and it gives you a 6-year risk of getting lung cancer. And behind that, the thing that's giving you this risk is a linear AI model. It is in fact an AI model. It's called a logistic regression model. The problem is this PLCOM 2012 is not a perfect model. It doesn't have 100% accuracy. It has an accuracy of roughly 80%. And I'm not going to go into what is accuracy here. We'll spend a lot of time on accuracy. So for now, just take it loosely. It is an accuracy of 80%, not 100%. And then the natural question is, can we make it better? Maybe using a more complex AI model. And in fact, without even doing this project or without even looking at this, I'm pretty sure we can make this better. Using a more complex model like a neural network, and you don't have to worry about these terms. You just have to know that there are these models, like a neural network or a gradient boosted tree, various kinds of fairly complex nonlinear AI models. And you can do that, and perhaps you can improve the accuracy. In fact, I'm pretty sure you can improve the accuracy of this risk prediction model. What is the trade-off to improving the accuracy? Well, there's two trade-offs. One is that the more complex your model is, the more parameters it has, the more training data it needs to learn. And why is that? The reason why that is because all the sort of obvious correlations that you have between features and labels have already been captured in most cases by the simple model. It's really the very subtle correlations that the complex model will capture in order to improve the accuracy. And in order to capture these very subtle correlations, it will need more and more data to have evidence for these correlations. And that's why the training data requirement goes up for more complex models. The other sort of side of this, the other trade-off, is that typically these complex models with millions of parameters are not very interpretable. Whereas in the simple linear model, the logistic regression model, you can ask the question, okay, if my risk is 85% for getting lung cancer in the next 6 years, why is it 85%? The simple model can answer that question for you and say, it is because you are 80 years old and you've been smoking cigarettes for 30 years. These are the two main factors why you are likely to get cancer. In the more complex models, this question gets more and more difficult to answer. And this is in fact one of the huge limitations of AI. This is an active topic of research, which is interpretability of AI models. But a huge limitation of AI, as opposed to other methods that could be less accurate, is that it is not very interpretable. Answering a question like, why is it like this, which we often get from stakeholders, they don't realize it is one of the most difficult questions to answer in the context of AI. Okay. The second example I wanted to give is, an example that we're working on, which is counting pests on a trap. Right? So again, there's a simple scenario and a complex scenario. In the simple scenario, suppose all pests that stuck to a trap would look exactly the same. They have a fixed shape, they have a fixed size, exactly the same type of thing. Then you don't need AI. All you need to do is create a template of that shape, and through a computer program, you can slide that template across the image, and wherever you match, you count it as a pest, right? Because all of them look exactly the same. You don't need AI to do that. You just have to match the template. But suppose the scenario is more complex, which it is in the real world, which is that all pests, even of the same species, look very different on a trap. Then there is no template for a pest. The AI has to learn some correlations, which are not easy to learn. And that's where you need AI. Right? So I'll end there. Happy to take any questions if people have time. But I'll end this slide for today.
But I have one question.
Sure.
Part where you said that not all models are equally interpretable, right? Just some models may give you lesser accuracy, be more interpretable. So would it be right to say that understanding upfront what your users need in terms of if it's nice to say that everything should be very, very interpretable. I should know how the AI got to this decision, but sometimes you don't need that. But some set of users need that. So that kind of influences the kind of model you would use. Sometimes it's not just the accuracy that you're looking for, but it's also the interpretability that you're looking for might be required, and hence you may choose a different model. So that what my question is that understanding required upfront, or or it's required
as far as possible upfront? As far as possible upfront, as part of the problem definition itself. It's one of the reasons in some projects when in the middle of the project we are asked, can you provide us an interpretation for the AI? The AI team is often balked and said, because it's a very non-trivial thing. In AI, interpretations are often method dependent. One method of finding interpretations may not give you the same results as a different method. So you have to do a lot of work to get consistent interpretations in an AI model. So it's very useful to define this upfront. In the computer vision projects we are doing, I think in most projects, some sort of interpretation is required, and that does constrain models to some extent.
Understood. Yeah, thanks.
Any more questions? Okay. If not, then we'll continue at this point, from this point in the next session. I'll decide whether we need an assignment now or maybe wait for another session before I have an assignment, but we'll work to create groups and so on and let you know. Okay. Okay, thank you everyone. I hope this has been useful so far.
Yes, it
Thanks,
really
Salman.
was.
Yeah.
Thank you.
Thank you.
Yeah, great.
Thanks, Alban.
Thank you.
Thanks.
Bye.
Thanks, Alban.